Okay, I'd like to welcome people back. This is the second part of our four-part discussion of network modeling in CompuCell today. We're going to do a very easy introduction to network modeling. This class will focus primarily on antimony model specification and not on the CompuCell integration. We'll talk about the CompuCell integration in the next module. As always, I need to remind you that the workshop is live streamed and recorded and distributed on YouTube. I've put the YouTube link in the chat. We'd like to thank our National Institutes of Health and NSF funding sources for their generous support. So today we're going to focus on running antimony network models and a little bit about how antimony works. There are multiple ways of specifying network models in CompuCell. We like antimony because it's easy to teach, but there are plenty more, and they're documented in the website if people want to dig more. And there also are material in previous workshops that talk about this in detail. There's a question about whether you should be loading the demo V2 or V3. I don't believe it matters. I think they're actually almost indistinguishable from each other. So you should be okay with either V2 or V3. Okay, we're going to talk about antimony usage and syntax. We're going to run a simple antimony model, and then I'm going to talk about how antimony works. And then we're going to play with it a little bit and develop some familiarity. And I'll give you some pointers on debugging antimony, because as we know, the XML has its own debug issues. The Python has its own debug issues. Antimony will have its own debug issues. Every time you introduce a new language, there are additional debugging considerations. I've already mentioned Herbert's great textbook, Introduction to Pathway Modeling. There is the antimony tellurium cheat sheet, which I strongly recommend people print out and have on their desk. There's also a great set of online documentation, telluriumreadthedocs.io, latest/quick start. If you search tellurium, network, and documentation, it should take you right to that page. There are a lot of network dynamics books available, and many books on the basic mathematics of what we're talking about here as well. Wikipedia has good things too. All of these are helpful. Network modeling is a big topic, a very big topic in its own right. I also recommend Herbert's archived videos as well on the topic. Here's a question: can we do practice on desktop? Yes, of course. Desktop or nanoHUB are equal here. I'm actually was planning on doing the demos on desktop today for this one, but it shouldn't make any difference. So we talked in the last module about some of the kinds of biological networks, chemical reaction networks, signaling networks, gene regulatory networks, transport networks, population dynamics networks, and outcome networks. All of these have the same basic structure, that you have species which are transformed into other species and whose rates depend on the components of the system. And I will remind you that the classic thing that we would describe if we're talking about chemical reactions would be a chemical reaction which goes, for example, 1 molecule of A plus 2 of B produces 3 of C, and we're always going to write a rate on top of an arrow. In this case, that rate depends on the concentration of A and B. I've assumed the law of mass action here. There is a rate constant, Kf, and we multiply by the concentration of A and the concentration of B squared. And as I said last time, this 1 arrow diagram generates three ordinary differential equations. One for the concentration of A, one for the concentration of B, one for the concentration of C. And I'm typically going to refer to concentrations, but if you want to think of A, B, and C as amounts, that's all right too. But then you have to also remember that your rates will depend on the concentration, and therefore you need to have volumes as well as amounts. Actually, antimony allows you to specify amounts and volumes if you choose. We tend not to do that because for the modeling we do for signals, typically you use concentrations. If you're going to do PBPK modeling primarily, you would typically use amounts and volumes. Okay. We like antimony because antimony has about 5 pieces of syntax. So I could teach you all you need to know about antimony in one 90-minute session. And you'll see inside of CompuCell references to SBML rather than to antimony or networks or tellurium or something else. And you'll also see the term tellurium and antimony paired together. Herbert Sauro, who was the originator of antimony and tellurium, although chunks of these were written actually by Andy Samoji, who used to be a postdoc here at Indiana University, loves to invent new names for things. And so we've used the name CompuCell now for 20 years. Herbert likes to always have a new name for each time he comes up with new software. And so we have to accept the fact that Herbert likes to generate new names. Antimony is actually the mole specification language, and tellurium is the package that interprets and executes antimony. There's also a back end which runs in tellurium and CompuCell called libRoadrunner, which actually parses antimony, turns it into executable code, and does the execution. So I apologize in advance if the terminology sometimes gets a little bit tied up. Typically, we will write antimony descriptions in text inside of our Python steppables. It's perfectly possible to write them using an external editor. Antimony and tellurium will run in a Jupyter notebook on their own. You don't need to run them inside of CompuCell. And there are other mole specification languages that they can be interconverted with, in particular, Systems Biology Markup Language, SBML. SBML is wonderful, but it's not really designed to be human readable or writable. You need an editor to read and write it. And that's an issue because I don't want to be teaching you another software package editor. You'd have to download it and run it. That's also a problem with CellML or MABOS. Again, I recommend looking at this tellurium guide. It says tellurium, but it's mainly about antimony. So we have to just be aware that the names are used more or less interchangeably, but antimony is the mole specification and tellurium is the software that implements it. So the first thing that we're going to do here is we are going to load and run a simple chemical reaction in antimony inside of CC3D. And we're going to write about the simplest chemical reaction we could. We're going to have a molecular species X that's transformed into Y at a mass action rate B times X. And we're going to have a species Y that's transformed back into X at a rate C times the concentration of Y. I didn't talk about this in detail, but I'm going to try, and occasionally PowerPoint or Word will betray me on this. In general, the regular format font letter capital X or Y represents the species, the chemical species, and the italicized version of that is the amount or the concentration. So capital X is oxygen, lowercase x is the concentration of oxygen. Okay, so we're going to load a little CompuCell program that will plot antimony models. Then we'll look at how to write antimony code, and we're going to then learn how to modify this little code, this little template. And I will ask your patience in not asking questions about how it works under the hood. Focus on the antimony specification for this class. And then next class, we'll worry about how CompuCell actually interacts with antimony. So now we've gone from 2 languages, CC3D, ML, and Python, to 3 languages, CC3D, Python, ML, Python, and antimony. Okay. So there are potentially a few people who haven't used nanoHUB before. I'm going to walk you through in 1 minute what you need to do. We have Tellurium V2. Pull down the Tellurium V2. Please upload it to nanoHUB. If you're using nanoHUB, use Jupyter Notebooks to upload it. Remember, launch Jupyter Notebooks. Click the upload button. Point to the file on your desktop or wherever you put it in your downloads folder. Hit upload again, and then switch back to CC3D and open the file. It will be zipped. You'll get a set of messages about unzipping it. You'll have to confirm the unzip. If it gives you an error message, you may ignore it. You may have to reopen it after it's been unzipped. Sometimes it will unzip and simply display on your screen. Sometimes you'll have to hit open again and point to it again. So I'd like everybody now to load that file and get it open. And let me do that too. And I'm going to do, people said last time that they liked split screen. So I'm going to do a split screen here. So let me reshare. Okay, I'm inside of CC3D, twit it. I'm going to open Tellurium V2. And I've got it open. And I'm now going to click on that and open the file. And I'm going to have to resize a little bit here so you can see everything. And I'll let everybody get that working. This is not a terribly complicated program, but at the moment I'd ask people to ignore the CompuCell part of it, and I want to focus here. And I'm going to zoom in a little bit. It's going to hide parts of the CompuCell, but I ask for your patience. I want to make sure that people can see the thing that's most important here clearly. I want you to focus now on the orange part of the code here. What we're going to be working for the next hour or so, hour and a half or so, will be lines 5 through 15 here. Maybe I can even zoom in one more time. No, that's as far as it goes on for me. Which says type tellurium model here. And then there'll be some text in orange. And down here at line 18, there'll be a line that says variables, X, red, Y, blue, and so on. And you may have to edit that line as well. Everything else in this code you will not have to touch for the rest of this lecture. Okay, so why don't you, as everybody, just run the simulation. So if you would, let us run the simulation. Now I'm going to have to do some resizing here, clearly. What you should see is what you see on the left. Is we've run the simulation, and now you'll see something that looks like this. You have a screen which says tellurium model variables with a plot. The x-axis should be time, actually, and you'll see a blank display for cells because there are no cells in the simulation. The dot size of these and the spacing may be different depending on the details, but you should be seeing a time series here. You'll be able to change the dot size if you like, and let us do that. I'll show you where to do that. If you go down back to your code for a second, and you go to line 36, it says self.plotWin add plot var styles dots, and then it says size equals 5. And if on your particular screen the size is too small, so the dots are too hard to see, or the dots are too big, you can make that number smaller or larger, okay? So whatever is good for your screen, because your configuration may be slightly different from the one that I have. Okay. If you are running desktop, let me come back to my display for a minute. I am going to now, we're not ever going to look at this cell field, so I'm going to resize my tellurium model variable so that it's easier to see. We talked about this a little bit the other day. If you're on the desktop and you have a plot that you like, as opposed to this one, which is a bit of a mess, if you right-click on the plot and you select export, it will pop up a dialog and you can export the image. If you hit copy, it will put the image into the clipboard, or you can export the data set. It's not going to work with nanoHUB, but on your desktop, if you see a plot that you like or you want to save the plot, you can do that. So I just want to remind you of that possibility. Okay, so now I want us to actually use this simulation a little bit. Again, we're only going to be playing with the code that's in orange here. Nothing else for this exercise. So why don't people try changing the value of C here from 0.01 to 0.1. Hit save all afterwards. And run it, and maybe in the chat tell me what you can do. Oh, yes. Gilberto says remove the grid from the graphs. That would be a good idea. You should please don't do that. This is just for me so that the display works better. So has anybody changed the value of that parameter and run it again? Did it change anything when you ran it? Okay, the lines changed, the graphs changed, good. What if you change the initial value of X and Y? You have 4 parameters here, B, C, which are rate constants. B is the rate at which X is converted to Y. C is the rate at which Y is converted to X. This X is the initial amount of X. This Y is the initial amount of Y. So you could, for example, start out with 1 unit of Y and 9 units of X if you liked. There's no reason that you have to make them add up to 10, but so why don't people just spend a minute playing with that change of rate constants? The axis labels are still bad, but at least it's not quite so ugly. Yes. So do people see something like that? Yes. So I have a question. If you change the initial amounts, does it change the final amounts? Assuming that the sum of the two initial amounts is the same? No. Okay. What about if I change B and C? If I change here, B and C are equal to each other. Suppose I make C 0.01 instead of 0.1. What's going to happen? If I make C smaller, am I going to increase or decrease the amount of X at the end? Try it out. Making C smaller decreases the amount of X and favors Y. And if I measured it carefully, I'd find out that the final amount of X over the final amount of Y was the ratio of B to C. I showed that quickly in the last lecture, but I didn't really go into it. Okay, good. So yes, so that's the result. The final value of X star divided by the final value of Y is C over B. Okay. If I multiply both B and C by 10, everything will happen 10 times faster, but it won't change my final value. If I divide them both by 10, everything will happen 10 times slower, but it won't change the final value. The final values don't, and the rates don't depend on the initial amounts. Okay, so now let's talk about antimony model syntax a little bit. Okay, antimony syntax is very, very simple. That's why we like it to teach with. There are a lot of extensions and decorations you can add to it, but the basics are very, very simple. The one thing that you'll find is there's one place in which it's different from Python, and that you have to remember that. But beyond that, it's actually really, really simple. Okay. So the first thing is that your model lives in a Python string. So your model is just a string, a text string. And so in CompuCell, or for that matter in Jupyter Notebook, you would define your model inside of triple quotes. Why do we use triple quotes? We use triple quotes because Python needs us to have triple quotes if we're going to have carriage returns within a string. It doesn't matter whether we use single quotes, single apostrophes, or quotation marks, as long as we have the same thing at the beginning and the end of the string. Okay. The disadvantage of having the antimony being a string is that error messages will be cryptic because there are no line numbers inside a string. There are line numbers in our display in Twit, but the string itself doesn't have line numbers. The model itself is just the code in the string. What's in orange here? Okay. So there are a couple of basic delimiters that we need to know about. A double slash is a comment. A hash is a comment. So the hash was not there originally, but that's borrowed from Python. You can put comments at the end of a line or on separate lines. A semicolon represents a break, and that could either be a break between lines or sections, and it's equivalent to a new line character. So I could, in fact, run everything together in a single line and just put semicolons wherever I have a carriage return. And if you're a C programmer or a C++ programmer, you will recognize that the semicolon comes from C. So syntax originally was based on C for this. It's a very old language. There was a previous incarnation of this language called Jarnac, which I think goes back 30-some years. The other thing that you'll notice is that there is a naming convention, and you'll see, for example, in pink here, J1 colon. And that names the reaction, the chemical reaction in this case, that follows it. There'll also be named events, which we'll come to in a little bit. That's a very convenient feature. It means that, in particular, the name itself is a variable which can be read. And so if we declare a name of a rate, the rate constant, the rate value will be available to us. And so, for example, if I look at line 6 here, I have first in line 5, a comment. These are my equations. Line 6, J1 colon names what goes on afterwards. X goes to Y. I will explain that in much more detail in a second. Semicolon, a rate law, semicolon, at the end of the rate law, and then a comment. This is rate law J1. Something that you have to be careful about. You don't have to name anything, but if you do name it, every name has to be unique. If I name 2 things J1, one of them will be ignored. The fundamental concept in antimony is a chemical reaction. Everything is built around arrows. And so if I want to write X goes to Y, I write X minus sign caret Y. So I basically draw the arrow. Since I can't write the rate law above the arrow in text, in pure text, I have a semicolon, and then I write my rate law. So if I want to write X goes to Y at a rate B times X, I type X goes to Y, semicolon, B times X, semicolon. That's it. Now, of course, I could have more complicated things in my rates. I'm allowed to have 3A plus 5B goes to 10C. So this allows me to write complex chemical reactions in a single line. Of course, my rate law might be a function of many things besides B and X. But that's all there is to antimony. Now, if you're going from, if you're starting out with arrow diagrams, this is very easy. If you're starting out with ODEs, it maybe takes a little bit more work to translate them back into arrows. Are there any questions about this basic concept? I mean, in some ways, antimony is so simple, it's almost frighteningly simple. You think there must be something more complicated when you look at it. It is. It is very friendly. Okay. So again, there's a direct diagram, a relationship between the arrow, X goes to Y, X goes to Y with a semicolon. I have to remember the semicolon. Rate Bx, semicolon B times X, semicolon. And each one of these lines affects 2 ODEs. X goes to Y will create a term in dx by dt where X is destroyed. And if I write Y goes to X, that will create a term in the X where X is created. And so here I have 2 lines specifying 2 reactions, and that generates 2 ODEs. Potentially, 2 lines could generate 20 ODEs if I had 20 components, and vice versa. Again, if I name the rate law like J1 or J2, that will return the value B times X or C times Y. So I have the right-hand side of the ODE, if I like, available to me. Okay. It's required in Antimony that any parameter be given a value. You're not allowed to not specify it. And so if I say that there's a rate law, which is B times X, and I don't give the value of B, Antimony will crash. And it's pretty easy, especially if you have upper and lower cases confused, or you have a lot of parameters, to leave one out, and Antimony will crash under that circumstance. It's a good practice. I haven't done it here because it's a purely abstract model, but I strongly recommend that after every parameter, you include the units. Millimolars per second, weeks, months, whatever the units of a parameter are, always type those at the end of a line. The initial conditions for a parameter, for variables X and Y, should always be specified. However, if you don't specify them, they will be set to 0. Something else is going to come up, which, well, I'll talk about that a little bit later on. What we're writing here is not computer code. It's a model specification, and that has some differences, and we'll come back to that in the next module. Okay, a couple of specific things that maybe follow from what we've just done, but are worth calling out. I've talked about sources. Suppose that I have something which is pouring A into my system at a constant rate. That would be arrow goes to A with a K on it for the rate, with nothing else, nothing on the source side. That is written, can be written literally, arrow goes to A, and that turns into a differential equation, dA by dt equals K. So I can write an arbitrary differential equation with the syntax arrow goes to A, semicolon, and then the rate. That's equivalent to writing dA by dt equals that rate. A sink, the simplest sink would be A decays at first order kinetics at a rate proportional to A. A goes to nothing. That gives me dA by dt equals minus Ka. And so you'll see sources and sinks. So you'll see dangling arrows for something that's being added to the system or being taken out of the system. If I want to keep track of how much is taken out, the integral of how much is taken out, then I'd have that arrow point to something and keep track of it. There are a couple of things that Antimony does, like boundary species, where it uses a $sign to lock the value of something, that we typically don't use in CompuCell, but they're available to you. I'm going to focus on the core things today that we need for CompuCell, and you can explore the other things on your own. If you want, you can write first order ODEs directly with a prime. If I write T prime equals beta times T times V, that declares dt by d time equals beta times T times V. That's functionally equivalent to writing nothing goes to T, semicolon, then the rate. The difference is that if I have the arrows, the system will automatically handle stoichiometry. If I use up 2 molecules of T to produce 1 molecule of something else, then if I use the arrows, that will be handled automatically. If I use the ODEs, I have to do it myself. And so I strongly encourage people to get used to using the arrow notation whenever possible. If you're taking ODEs that were written by somebody else, then you can always type them directly into Antimony. But I'd recommend spending an hour translating them back into the arrows they came from. In biology, you almost always have arrows, not ODEs. There's another reason for that, which is that you can solve these rate diagrams stochastically as well as deterministically, and that's not going to work with the ODEs so well. If I have multiple rules affecting the same species, they add. So I have nothing goes to T, T plus V goes to I1 goes to D. All of those components will sum up to generate the ODEs for the system. And if we had more time, I'd give you a little exercise where you practice translating back and forth between the arrow diagrams and the rate equations. Okay, so we'll do some simple exercises with Antimony now. And I would ask people, please save what you're going to do locally, because you're going to need this in the next module. So whatever you do, make sure you save your simulation somewhere where you remember where you put it. So you'll have it available in an hour, okay? Okay, so the first exercise is take the code that we had, which everybody has running, and I want you to change this now. Before we had A goes to B, and we had X goes to Y, and Y goes to X. And now I want you to change that based on what we've learned about Antimony syntax. Have A go to B at a rate Ka times A. B goes to C at a rate Kb times B. C go to D at a rate Kc times C. Start with 10 units of A. You can start with 10 units of A and B if you like. And make B, C, and D 0. Actually, sorry, this is a typo. What I wanted to say was A equals 10, B, C, and D are 0 to begin with. And you can try out Ka, Kb, and Kc all equal to 1. And then you could make them either 1, 10, and 100, or 1, 0.1, and 0.01. And the one thing you're going to have to do is at line 18, where it says variables, you'll have to change the name there. Instead of X and Y, you'll have to type A, B, comma, quote, C, close quote, colon, and then a color name. Okay? See if that works for you. Give people a minute or two to try that. And I'll code along. I'm not going to talk through it, but I'll just I'll do the typing while you're doing it. But please try it on your own, and don't watch me do it. But it's not too hard. Everything you need is here. See if I make a mistake too. Oh, one thing in Antimony, indentation does not matter, but I recommend respecting indentation conventions just for readability. So there's a question on color options. Do you mean color options for the plot or color options for the display in the editor? I don't actually know the list of all possible colors. I know red, green, blue, white, brown work. I haven't tried teal, aqua. Somebody could try and see if it works or not. So I'm going to do a poll. If you're done, click done. If you're not done, don't click anything until we're ready to go on. But if you're having trouble with something, please do ask. So the question, should Antimony is great for simulating things like SIR models. In fact, you'll see some of the slides have SIR models in them because in 2020, we retooled all of our courses to teach infection and immune response. And so all of the Antimony demos were SIR models, viral replication models, and so on. And then starting in 2022, people said, we're tired of modeling viruses and immune response. Can you please go back to the old system? And so we switched everything back. But occasionally you'll see, actually one of the slides I just showed was a viral infection model, beta times T times V. Beta times the uninfected population times the viral load, where beta is the infectivity of the virus. So you'll see an occasional slide that's left over from the COVID era. But yes, it's a great way to write SIR models. And there are a bunch of published SIR models in Antimony. And I taught 2 years worth of courses on, all on viral infection models. So we have a big archive of them if you want. Okay, the people who say they need more time, do you need anything? Can I do anything specific to help you out? If you have a question, put it in the chat. Otherwise, I'll give you 2 more minutes. Again, what I'll try to do for these kinds of simulations is I'll have the base simulation and I'll wait to try to get everybody through that as much as possible. And then at the bottom, I'll have something like an extension or a challenge exercise. So if you're done with the base simulation, try changing the values of Ka, Kb, Kc. If you make them harmonic functions, 1, 10, 100, or 1.1, 0.001, you actually get some quite interesting relationships between the values and the times. It's not so clear. It's not so clear maybe if you only have 3 chemical species, but if I had a cascade of 10 of these, and then I used harmonic sequences for the values of the parameters, it gets to be quite interesting. So let me see if I made any mistakes when I run this. Let me go back to my simulation. Let's try. So yes, that looks a lot like an SIR model, doesn't it? Okay. Okay, great. Okay, so you've written a chemical reaction. So this is what we got. So there are a couple of things that I want to talk about antimony. One thing you have to be a little bit careful about is that antimony has some reserved words, which you cannot use as variable or parameter names. And if you do, antimony will die, and it will not always generate a informative error. It's not so surprising that time is a reserved word, because time is the time in the simulation. But gamma is a reserved word because gamma represents the gamma function. And so if you're going to type something like gamma, call it gamma 1. Don't use delta without a 1 after it. And so do try to be careful about naming variables and parameters something that's not likely to infringe on a reserved word. This is not the most powerful system in the world. It does believe if you want to find steady states or plot phase spaces, Mathematica is much more powerful. Octave is more powerful. Nonlinearity is okay. What you can't do is have higher order derivatives. So there are definitely limitations here. One thing about antimony, though, is it's portable. If you translate it into SBML, which you can do, SBML is a modeling standard, and so it can be read by dozens or even hundreds of different packages, and it can be modularized and used as a component. So some of the things that make antimony a little bit inconvenient, some of its limitations come about because it's designed to be very reliable. Another thing you have to worry about a little bit is if you have missing parentheses. Tellurium will tend to die with uninformative errors. So you do have to be careful to make sure your parentheses match. If you have your simulation just die when you write antimony, just die, I really recommend doing something that is very basic, but it surprises me how often people don't think of it, which is to comment everything out. All right, a comment is a hash. Comment out all the lines. You have to be a little bit careful because if you comment out the parameter definition, it will crash. So you would have to comment out all the lines that you're not using and see if it runs, and then add them back one at a time. It's not elegant, but it works. That's usually if you have antimony crash and kill everything and goes and CompuCell goes poof. Usually it's either a mismatched parenthesis or that you used a reserved word as a variable name, and that'll find it for you. So not very okay. Can we add step functions? Yes, that's going to be the next thing we're going to learn how to do in antimony. Yes, you can. There are two kinds of step functions. One is you can have piecewise linear functions. And that I'm not going to cover, but in the antimony manual, you can define functions that are not functions like max and min work. Theta functions work. So those work, but you can also have events in antimony, and I'll come to that in a second. The other thing that if we were running antimony by itself in Jupyter notebooks, which is not so convenient to do inside of CompuCell, is if antimony doesn't have a syntax error but crashes when you run it, that's usually because of either a divide by zero divergence. And so if you're going to run it freestanding, when you simulate for a tiny amount of time and ask, does it crash? And then a little bit longer and ask, does it crash? And then a little bit longer. And then if you can find the time at which the crash happens, that will usually tell you what variable diverged or what value went to zero with the divide by zero. So those are sort of simple principles for debugging. They apply to CompuCell as well, but they're particularly valuable in antimony because the model itself is a string. And so you don't get some of the debugging on syntax that you would get with a regular parser. Okay. So our next exercise is called chemical equilibrium. Take the code that you just wrote, add one line to it, and now have D wrap around and turn back into A. And tell me what happens. That shouldn't take very long, I hope. You'll have to add one chemical reaction after line 8, and you'll have to add one parameter. I'll do it with you. Now, easy cut and paste error. If I kept this as J3 instead of J and didn't change the name, it wouldn't work. I can't have two names with the same label. If I ran this now and hadn't defined KD, it would crash. That would probably give me an informative error, though, rather than just a disappear. Were people able to get that to work? I don't want to run a poll and force everybody to have to start have that interrupt. So, did that work for people? Does anybody need more time to do that? I'll show you the code again in a second. I just want to make sure I did it right. How is that different from what happened before? Anybody? Do people remember what you got before? Do people need to see the code again? All species reach equilibrium, that's right. And they become non-zero. Does anybody need more time? Does that work? If you've got that working, you can change the rate constants or change the initial concentrations. So yes, before we wound up with all D and everybody else went to 0. Now we wind up with everybody here equal. That's because I set my parameters all the same. If I set one of these bigger, make say Ka bigger. And now let's see what happens when I run it. Notice that making Ka bigger, I eliminate A faster. And so now I have 1/10 as much A as I have of everything else. And so this is very simple, but one can use this kind of simulation to develop a really nice intuition about simple chemical reactions. Okay. So one of the things that I mentioned is that I can write quite complex chemical reactions in antimony, which would be a pain in ODEs. So suppose that I had 2 molecules of A plus 3 molecules of B going to B. I simply type that. And antimony will handle all of the bookkeeping of creating A on one, deleting 2 molecules of A per reaction rather than 1, 3 molecules of B rather than 1. It'll handle the fact that I'm deleting B on one side and creating it on the other. And so this is very powerful if I'm really writing chemical reactions, because I don't have to remember all the bookkeeping. It's done for me automatically. The one thing that you have to worry about is that when you do exponentiation, antimony comes from C, and so it uses the caret for exponentiation. So if I wanted to write mass action here, mass action would be A squared times B to the 3rd. And so I have to remember to use the different exponentiation operator. Most of the standard text functions, min, max, sine, cosine work in antimony. It used to have pretty good random numbers. There was a new release of antimony that broke it some years ago. I believe they're fixed now. So I believe the random number generators, if you want a gamma distribution, you want a Poisson distribution, it'll work. But that's something you may have to check with the details of the simulation. So here I've typed some complex chemical reaction. I did that more or less at random. I have no idea what I'm going to get when I run it. Nothing very interesting, it looks like. Why not? What did I do? Oh, because this now depends on B. If I start with no B, there's no reaction. So now let's try 5. Remember what I said about not writing code until you've thought about what you're doing. So here I'm not following my own advice. It's not very interesting because the reaction initially is very slow. You're seeing a little bit happen. Again, I picked something at random just to show the code. Okay. So why don't you try writing something a little bit more exciting than that? Just try, again, just write 1 or 2 lines where you write something which is a non-trivial chemical reaction. In this case, Ka is the rate of A or the rate of 3A plus 5B. Okay, so that's a good question. The rate is the rate for the reaction. And so in 1 time unit, I destroyed 2 times Ka times A squared times B cubed of A. That's another reason that the reactions are better to write than the ODEs. So think of this as the number of reactions occurring per unit time. And so if you're using up 2 A's, then the number of A's taken away is twice that. Again, if we had a little more time, I have a little exercise that practices that. Okay. I don't want to take too much time with this, but just try typing something of this kind here and seeing that it runs. Don't take the time to do something complex like what I wrote here. Don't want to take that much time. Because there are a couple more things that I want to play with before we go for it, before we run out. Okay. The one thing that might be unexpected is that if I want to say that I'm using 2 molecules of A, I don't write a times here. I just write the number and then the variable. So one thing that this means in particular is that variable names cannot begin with a number. They can't begin with a special character either. Yeah. Oh, well, maybe K1 is a better name. I didn't want to retype. If I type K1 here, I have to remember to type K1 there. Good point. Any other questions about that? This is something, in a sense, you can try on your own. I think the key point is that even if I have quite a complex chemical reaction, it's only typing 1 line. These rate laws can become quite complex because they'll often have Hill functions, or they may be products of different things. Something I'm not going to tell you about, you can look up in the antimony manual, is it does have function definitions. So if I want to write a Hill function, I can define a Hill function and then apply it repeatedly. You created something that generates infinite amounts of A. So what could generate an infinite amount of A? Well, in general, these things should be conservative. Let's see. Sharon says, I seem to generate something that's creating infinite amounts of A. And so Sharon wrote, J1 is 3A plus 5B goes to A plus 2C plus 7D. And the rate is KA to the third plus B plus KB to the fifth. So that's a very interesting rate rule. This is not respecting mass action. So if I look at the rate that you typed, which is where you've summed the two rates, one of the things that you typically want is that if you run out of B, the reaction should stop. If you run out of A, the reaction should stop. And in the case that you've written it here, that's not going to be true. Yes, Pedro gives the mass action rate. Now, of course, we can write things other than chemical reactions using this notation. So it's perfectly legitimate to write a rate law that doesn't obey mass action. In general, we expect that chemical species don't go negative, the concentrations don't go negative. But there's nothing that says that the rate laws that we write couldn't be things that go negative. One of the variables might represent the electrical potential, which could be a positive or a negative number. And so, my net worth, I could spend money and go into debt and have a negative net worth. So it's not a universal truth that the rates have to go to zero when the values go to zero. But if we're talking about things like populations, chemical concentrations, then we would expect them to go to zero, if the rates to go to zero if the values go to zero. So there's a question, can I write a reaction that depends on the derivative of another species? So this is an issue. And the answer is, I could write legitimately. Actually, I haven't tried this, but I think I can write. For example, J3, once I've declared J3 is the time derivative of C in this case, minus the time derivative of C. I believe if I type J4 here, sorry, not J4, I can't be self-referential, J3, that should work. So let me try that. I haven't ever done that. That's a great question. Let's see what happens. Let me fix this back to being just A plus B. So it's not something quite so ugly here. Does that work? So, or does it crash? Yep. So that's legal. So yes, you can reference the first derivative of something. You taught me something. Great question. What you can't do is have a time delay. I can't reference what the value of something 20 minutes before. That I cannot do. And this comes back to this idea of state and process, right? The whole model description framework that we went over last week at the beginning of the course had this idea that you have some objects that have a state and a set of processes now that describe how they evolve in time. Their history, unless you've attached their history to them in some way, is not accessible to now to do the dynamics. And that's why delay equations are problematic. They're actually philosophically problematic as well as mathematically and computationally problematic.